Good afternoon all. This video is basically on the nematic superconductivity, and the material has been chosen in this LAO ATO in the 1-1 direction. So this presentation will be covered under the outlines. First, the introduction of nematic superconductivity, relation between nematicity and proximity superconductivity, background of the mechanism, progress of nematic superconductivity along with topological aspects, discussions, conclusions, and future scope of the nematic superconductivity. So in the introduction, let's start with the very basic. The first, introduce what is the nematic superconductivity. Let's introduce the word nematic. Nematic basically refers to an ordering of the particles. So it is directional dependent, not arrangement of the positions. Type of superconductivity. It is directional dependent superconductivity, means if we measure in the different direction, the superconductivity results are different. This breaks the rotational symmetry, preserves translation symmetry but not always, and translation symmetry is not most important in the nematic superconductivity. Anisotropic superconductivity gap, the gap in the superconductor is not same in all the directions, the gap are in the different, indicates unconventional pairing mechanism. And the important part of this is that if a material is highly rotational material, like the perfect cubic crystals, and if we rotate the cubic crystals, it has higher rotational symmetry. But it is important that if the material goes into the momentum space, it breaks the symmetry, rotational symmetry, like many kind of the distortion, like ferroelectric distortions, and it changes either the symmetry, like goes into the different crystal structure. It also breaks the symmetry, like tetragonal and many others. So on that time, the cubic crystal break the rotational symmetry, and it also breaks the superconductivity. So how is it different from the normal superconductivity? So in the conventional superconductivity, the gap is isotropic in all the directions, like this is the sphere in the S-wave superconductor. If I rotate this in any of the directions, so there is no any kind of the rotational symmetry breaking, means to say that the sphere, this has the infinite rotational symmetry. But if this is the real space, and if we are comparing with the nematic superconductors, the gap are anisotropic gap, and this is the different in the different directions. And like this, the p wave and d wave superconductors, they are not gap in the all the same directions, like the p wave in the px, py, and pz, they are the different directions, and the superconducting gap is different. So this breaks the superconductivity, and this is the nematic superconductivity. So the comparison is that the conventional preserves the rotational symmetry, but nematic superconductors breaks the spontaneously rotational symmetry, and this conventional superconductor strictly follows the BCS theory, but nematic superconductors not follows the BCS theory because unconventional pairing mechanism. So the symmetry role and with the superconductivity, the translation symmetry, like this, the translation symmetry, if the superconductors preserves the translation symmetry, the superconductivity preserved. And again that if the system breaks the translation superconductivity, also the superconductivity still remains in the materials, like many of the crystals break translation symmetry, like ferroelectric materials, but they also preserve the superconductivity. But in the rotational symmetry, if the system breaks the superconductivity, means to say that if this preserves the rotational symmetry, it preserves the superconductivity. This is the real space view, and one another. This is the rectangle, like breaking the superconductivity, because in the rotation the symmetry is not same. This is the two-fold view, and this is the two-fold structure. And the one important thing is that this is shown in the real space, and the superconductivity is breaking here, like that you are seeing that the crystal structure is not same on the rotation. This is the C2 fold rotation. So the superconductivity is breaking, but in the above one is that if you are looking here, this is the C fold. So the superconductivity still preserves, the rotational symmetry is not breaking, but in it the superconductivity is breaking, and because this is the C2 fold. Also, like this in the structure, uh, this is preserve the superconductivity. If I rotate this crystal C6 fold, so this preserve the superconductivity, but these are the elongated structures, because this blue and yellow, this blue and red are not same. So if I rotate this crystal, this not preserve the C6 fold symmetry. So this preserves the, so this breaks the superconductivity, and this is not in the rotational symmetry case. This breaks the rotational symmetry, also breaking the superconductivity. And this is the band structure view, like the in the momentum space. So this is the crystal structure, this is the is circle like that, this is the spherical, and if I rotate any of the kind, so the superconductivity preserve means to say that if I replace kx and ky, there is, we cannot identify which is kx and ky. So we can say that if any of the rotation, this preserve the superconductivity, means to say that the crystal structure is same in the momentum space. And this also, we are looking here, this is the like a ellipse. If I interchange kx and ky, we can easily identify we have changed the axis. So, and I rotate these crystals like that. If I rotate these crystals, uh, and we can say that after 180-degree rotation, the symmetry is same. So this is the C2 fold symmetry. And in the band structures, this also presents that seeing, or we are looking here, the crystal structure, the symmetry is breaking, because there is the splitting in the band structures like that, and there is the difference in the band structures in the color contrast. So this rotation symmetry, it still, it states that the symmetry is breaking. The system is no longer in the C6 fold symmetry, and with this that we can also looking like that the symmetry breaking results are like uh, this way. The rotational symmetry, the kx and ky axes are not same. So the kx and kxy axis in the direction, the crystal structure is not same. So one is elongated, and the difference is that we are looking, you can easily identify by this animation. So this, the crystal structure is breaking like this at the end. If we rotate the crystal is again not in the C4 symmetry. So this breaks the superconductivity, so because the crystal structure is not same after the C4 rotation. So one of the results of the di over dv has been shown here at the particular magnetic field, and after the rotation of the 180 degree, the results are repeated. So this states that the C2 fold symmetry in the crystal structure, if this preserves the C6 fold symmetry, so after every 60-degree rotation the results are same, but here the results are not preserved the same, like this is spontaneously break the superconductivity, like this change from C6 to C2. So this is the anisotropic superconducting gap, and the for isotropic the system should be repeat at every 60 degree. The peak should be same, but here the system is at after 180-degree rotation. So this shows the C2 fold symmetry, and this breaks the nematic superconductivity. So relation with the superconductivity is that with the proximity superconductivity and nematic superconductivity, the similarity are looking like. So there is no direct link between proximity and nematic superconductivity. If superconductors are nematic, induced superconductivity may be nematic proximity. So with the topological superconductivity, what are the relations like that? So the concept is that the proximity is topological proximity superconductor plus nematicity. So the description is that the coexistence of topology and isotropy in induced superconductors, and possible regions enables direction control over topological modes, means to say that if the material is the nematic superconductor and if we measure the superconductivity in the different crystal axis directions, either the longitudinal and transverse, so this also shows the proximity as well as the nematic superconductivity results, means to say that this shows the superconductivity and breaking of the superconductivity. So the similarity is that so both are the unconventional mechanism, they not follow the BCS mechanism and they may host Majorana modes. So this is the background over the nematic superconductivity with the results has been shown here. So first is the elastoresistivity. So the resistivity can identify the nematic superconductors if we measure the superconductivity in the different crystal axis directions. So the superconductivity results are different, means to say that the elasto means to say that the resistivity like the strain dependent like resistivity, and there is the very large change across the nematic temperature in the resistivity in the different crystal axis direction. So this is the strain parameter, and this is showing the very large change across the nematic temperature in the resistivity. So this is the elastoresistivity. And this is the lattice distortion means to say that if a material distorts their lattice and it goes into the different symmetry, so with this showing the very large difference across the nematic temperature where the symmetry is breaking. So with that, like in the animation this has been shown here. So if I stress this perfect cubic, this has been shown here, and if I stress like along the x-axis and y-axis and after that I rotate this crystals, so this node preserves the C4 symmetry, so this breaks the C4 rotational symmetry, and with that the system showing the breaking in the superconductivity after the breaking of the rotational symmetry. And another, the Raman measurement also identify, this is the very powerful tool to identify the crystal structure breaking, the crystal structure like at the low temperatures and over the other temperatures, if a crystal structure going from one symmetry to another symmetry, so the Raman can easily identify. And this is the quantum elastic peak have been observed across the nematic temperatures where the crystal structure goes into the different one. And with that in the susceptibility the atoms are arrangement in the different directions and they are the different one, so that's why the in the susceptibility across the nematic temperature this showing the very high peak, so this indications that the symmetry is going in the different direction. And this is the ARPS measurement with this showing in the DXZ and DYZ atomic band structure calculation. So this states that the bands are splitting and they are showing the symmetry is not same in all the directions, the symmetry is breaking, and with that the energy across the nematic temperature, so there is the anisotropic change in the energy, so this also states that the band structure calculation also easily identify the nematic superconductivity, the bands are splitted and they are no longer in the rotational symmetry, they are no long more in the rotational symmetry, the bands is splitting, and with that the superconductivity is breaking. So this the ARPS easily also can identify the nematic superconductivity because the bands are also not same in all the directions. And progress on nematic superconductivity with the topological aspects. So this the crystal structure break the C4 symmetry, and the authors are measured the resistivity in the two different directions of the crystals with the 0 degree with the current and with the perpendicular current. So they are changed in the upper critical field, and with the upper critical field, the upper critical field is increasing in the transverse direction. So this state basically that the upper critical field because of that, the many times like the due to the Zeeman splitting, the spins are in the upper band more compared to the lower band, so thus they are not the symmetrical. There is an anisotropy, and one of the important thing is that the orbital effect, the spin orbit coupling, affect the upper critical field in the transverse direction. So with this, that there is the large change in the upper critical field. And they the anisotropic like the band structures with the topological materials, the band structures like this across a drag point. There is the conductivity like on the surface states, and there is no conductivity in the bulk. Because of that, the intrinsic magnetic field in the materials, due to which they orbiting the like cyclotron orbits inside the materials, and the inside the bulk is not participating in the conduction, and only the surface are the contributing. And this is the superconductivity band diagram like that. Across the uh, Fermi energy, the density of states suppress, and they are uh, compared to each other, uh, collision, and the showing the superconductivity. And in the superconductivity transit topological materials like this, the band structures of the coincide like the topological materials, and superconductor materials also showing the topological superconductivity. The surface is in the superconducting dominations, and the bulk is not participating in the topological superconductivity. So this is again the pneumatic superconductivity role of the top with the topological materials. This is the superconductivity with pneumatic, and this is the metallic. So there is no role of the metallic either to rotate in any of the directions. So the metallic materials are not dependent on how to break the rotational symmetry. The pneumatic, this is just closer to the superconductivity, and this is the quantum region. This is the quantum metallic region where the results are also affected by the pneumaticity, like the if the rotational symmetry is changing. So the just across the value of the superconductivity, the results are also affected due to the quantum effects are here. And this is the superconducting plus the pneumatic behavior with the rotational symmetry breaking, the superconductivity breaking. So the on the rotation of this, they are all not same over the rotation. The superconductivity is not same. So with this, that the elasto restriction, the magneto restriction, this shows the superconductivity uh, is changing with the change of the with the magnetic field. The materials change in the direction of the length, like the if the material is the cubic, so the cubic is not along the perfect cubic with the magneto restriction. Like this, the direction is um, elongated the crystal structure with the magnetic field. So with this, that the directions, the ABC parameters are not same. So if the with the rotation, so this also breaks the superconductivity after the rotation under the magnetic field. So magnetic field also can break the superconductivity. So if a material no longer in the superconductivity state, and this is the graph also shows the symmetric plus the pneumatic behavior. This is the order parameter with the temperature. The superconductivity is suppressing, and this is the superconducting pneumatic and pneumatic materials. This is just closer to the value of the superconductivity, and here the material in the quantum uh, metallic state. And with this, that this is also affected by the rotational symmetry, and the results are also decreasing. This is the Q0 parameters indicates the results are decreasing with the temperatures of the pneumaticity, and just the material reaches into the metallic state, so there is no effect over the pneumaticity. So in any of the direction you rotate the crystal structure, so there is no effect of the breaking of the symmetry. So the metallic behavior is all same if you measure either of any of the direction and any of the crystal axis. So you measure the resistivities and any of the results, so they are all same in the metallic states. And this is the susceptibility, and the diamagnetic behavior is showing in the superconducting states. So this is the showing the susceptibility parameter. So the less than in the negative direction, and this showing the superconductivity behavior and with the nematicity. And in the quantum metallic region, the susceptibility is increasing and there is no more effect in the metallic region. And these results are very well with the theoretical results. So the discussion of these materials interfaces, why the authors are interested in these materials. So these materials have very high mobility at the surface and 2D electron gas at the interface, and also give the SDH oscillations, weak antilocalization signatures, and many other of the quantum interference effects like 2D electron-electron, 3D electron-electron interactions, and various kind of the electron-phonon interactions at the low temperature. So this material is interesting by the transport measurements, and this is also in tested materials by the spin orbit coupling, because these are the heavy elements like the heavy ZT elements, and high Z means they have the high robust spin orbit coupling, so they also shows the Raspberry spin splitting and dielectric properties over the higher temperatures. And inside of this, the materials are very interesting. The results of the superconductivity and magnetism, and the authors are interested in these materials because this material shows the nematic superconductivity, and in the nematic superconductivity there is the crucial role of the KTO surface orientation in the different directions, and so the authors are very much interested in the nematic superconductivity over these materials, and they have measured. So this is the discussion of the measurements, like the authors measured the resistivity in the uh, different axes like the longitudinal, and this is the transverse directions, and this is the schematic diagram of the resistivity measurements, and these are the results like the longitudinal resistivity, and this is the transverse resistivity. And one important thing of that, the in this B graph they are showing the current density graph, and with this that, because the current is a scalar quantity, and with this the current we cannot clearly saying that the superconductivity what are in the transverse direction either in the longitudinal direction. So with this that the authors measured the resistivity by the current density, and they had extracted the results by this relation, and with this that the clearly longitudinal and the transverse resistivity, and this is the longitudinal resistivity which is showing the resistivity is 0, and in the transverse direction where the rotational symmetry is breaking, the resistivity is not more 0. So here if you are looking here, the results are showing the 0 resistance, but in the clearly mentioned in the paper, so the resistance is not 0, and you can also clearly see in the magnetoresistance these results, and the authors measures the resistance across a particular direction of the to rotate the crystal at a particular angle of the 141 degree, and to observe in the longitudinal and the transverse directions of the superconductivities. This showing the very beautiful results of the nematic superconductivity. And this is the Gauss symmetry where the superconductor clearly breaks the Gauss symmetry when they reach into the superconducting states. Means to say that they not follows the like Maxwell equations. Because of that, just if you there is no when material goes into the superconductor state, this expels the magnetic fields. If the magnetic flux 0, so it also required to the electric field also 0 in the superconductor, but according to the Faraday's equations like that, so this the Faraday equation showing the electric field is constant there. So this is not possible in the superconductors. So this equations not follows. So the Gauss symmetry is breaking, and means to say that again the London brothers to modify these equations for the superconductors. So this is the longitudinal axis, and in the longitudinal direction the resistance with the angle resolved resistance, to rotate the crystal axis directions, and at a particular value of the 1.55 Kelvin, this showing the superconductivity, and this is the C2 fold like behavior, because if in the longitudinal direction if you rotate also the crystal axis, so this also breaks the superconductivity, and this is basically showing the very beautiful results of the nematic superconductivity. And if you are looking here with and comparison with the uh, transverse results, there is also the change in the signatures are looking same, but there also must change across here. So these are not uh, just same. So this is the anisotropy here, but here there is no anisotropic behavior. This is the mixed of the isotropic plus anisotropic because of the rotation, because every crystal not like behaving a perfect one. So with this that, and in the transverse case this is breaking the symmetry always, and this is the anisotropic kind of the behavior, and there is a negative resistance we will discuss later. In brief, what is the comparison between E and F? So because the signatures are looking same, then what is the difference? So the difference is that if you are looking here, so if you are looking here, so there is just across the showing there is a different kind of the results. They are looking same, but they are not perfect same. So this basically states that in E and F there are the difference between is that uh, this is the F is the completely anisotropic. In the transverse measurements they have been taken the results, and in the longitudinal resistance with the rotation of the crystals, this also breaks some kind of the symmetry, and this is not showing the every time, this is showing zero resistance. So for these measurements, if a crystal is the perfect cubic crystals, and like in a perfect cubic crystals, we also rotate the crystals. So perfect cubic crystals also break the superconductivity, and it also may be the nematic superconductor after the rotational symmetry. Because of that, many of the crystals breaks the symmetry in the momentum space. They are looking the cubic, but in momentum space they are breaking the symmetry, and that's why they shows the nematic superconductivity. So this is the nematicity graph, and in the metallic region, uh, over the higher temperatures there is no change, because the pneumaticity node depends on the metallicity, and in the if a metal in the metallic state, so there is no meaning of the pneumaticity. If you either any of the direction you uh, take the resistivity, so there is no effect, the results are same. But in the superconducting state and in the quantum metallic region state, so this effects, and the results are compared to the four-fold rotation. In the two-fold rotation, the pneumaticity parameters is very high in comparison to the four-fold rotation, because in the four-fold rotation pneumaticity is more compared to the four-fold rotation. So these are the because of the many thermal resistivities, the isotropic breaks to anisotropic, and alpha beta parameters are the pneumaticity angles with the response of the crystal directions rotations. So this is the pneumaticity results have been discussed in the authors have been discussed in the paper. In the superconducting region, the results are very much affected with the magnetic field, and they are suppressing very fast response. But in the metallic regions, so there is no low mode change. The results are looking same. They are the means the parameters are suppressing, but the results are features are the same. And the over the different magnetic field, in the longitudinal resistance, with the angle dependent, the resistivity has been measured, and they are showing the superconducting results at very low magnetic field, and over the higher magnetic field the superconductivity is breaking, and this showing the anisotropic kind of the behavior, because over the higher magnetic fields So this is showing over the rotation, also the cubic behaving means to say that the crystals is not in the perfect rotational symmetry states. They break the symmetry over the rotation also in the longitudinal direction, and they are compared with the transverse results. The superconductivity is breaking here. This is not zero. Authors clearly mentioned in the paper. And the negative resistance is basically due to that if I rotate the crystals, and because of the current goes into the lower resistance regions, and the measured and showing the results are not of that. Because of that, the results are showing the pneumatic axis, and on that cases if I rotate the crystals, and because of that the current is going into the lowering path of the resistance. So this showing the current is not passing this axis. It may be that this showing the negative resistance. Now this is the discussion. This is the contour plot discussed in the resistivity of the magnetic field, and they are the different regions. This is the superconductivity with the temperatures and the magnetic field. The superconductivity is suppressing as normal, and this is the metallic states with the magnetic field. The resistance is continuously increasing, and because of that the quantum confinement is increasing. The with the magnetic field, the magnetic field rotates the direction of the electrons, and it trying to confine the electrons at a particular region. And with this that the normal in the normal state case the resistance is continuously increasing, and these are the important like below and this one quantum mean fluctuations and the quantum metallic state. With the temperatures and the magnetic field the resistance are increasing, and in the second one you can also observe that the pneumaticity is increasing also in the quantum metallic states. So with the magnetic field and the pneumaticity is increasing. So this is the important, and this discussed that. So the quantum metallic region just close to the superconducting, this is also affected by the pneumaticity. If I rotate the crystals in the different crystal axes and either the longitudinal and transverse, we are comparing that. So the quantum metallic region also affected by the pneumaticity, and this is the superconductivity. And so here in the pneumaticity is more, and this is the normal effect. So this showing the zero pneumaticity. So normal metallic states there is no effect to the rotation of the any kind of the rotation. So in any of the crystal axis you have taken the measurements, so there is no any effect in the normal metallic states of the pneumaticity. So the conclusion is that the angle resolved resistance clarifies the pneumatic signatures through rotational symmetry breaking from C4 to C2. So this is the comparison like that. In the complete C-fold rotation, so the resistance is zero, or either you any kind of the, so this is basically this is not TK, this is phi. So if you rotate the crystals, the resistance is completely zero. And in the pneumatic structure, like when the superconductivity is breaking, and this is twofold, only the region of this angle, the superconductivity is zero, and either of that there is a finite resistance value, either the resistance is increasing and over decreasing, but only just this region where the metal in the C2 folds states the superconductivity is there, and this breaks the superconductivity and showing the pneumatic superconductivity results. So this is the mistake. This is the phi. Resistivity measurements along the longitudinal and transverse current direction proved the pneumatic signatures due to zero and non-zero resistance C4 break. The rotational symmetry is breaking, and in comparison to the longitudinal and transverse directions, the superconductivity results like that. So if you rotate the crystals in the like x-axis, the symmetry is same. This is the C4 symmetry. But if you rotate the crystal structure along the y-axis like this, there is no more symmetry, C4 symmetry. This is the C2 symmetry. So the superconductivity results are breaking. Again, the conclusion is that the nematic parameters, there is a sharp peak at zero magnetic field and it disappears under magnetic field, confirms a transition from an nematic superconductivity states to more isotropic metallic states. If you are looking that there the in the metallic state the pneumaticity is almost constant, showing the results, but in the superconducting regions there is the very sharp transitions. Both magnetic field and temperature drive the transition from the superconducting phase to the quantum metallic, highlighting the emergence of the pneumaticity. And you have clearly seen there in the metallic state there is no much more effect of the pneumaticity. And with the angle dependence, the measurement have been taken at the 40 millikelvin temperature and comparison with the superconductivity and indicate the superconductivity with the suppression of the magnetic field and negative resistance in the transverse resistance due to anisotropic, possibly due to vertex motion or phase homogeneity. Like it means it may be that these are the possibilities if we are measuring the resistance in a perfect direction of the structure, but because of after of the rotation the current basically favoring the lowering resistance path and we are looking the results of the different region, so it may be that the current is not going, and when the current is not going in that direction it may be showing the negative results. So like this is the x again of the y. So again of y, this is not showing the superconductivity is breaking here. So this is the overview of the paper. So the authors give a strong message through the transport measurements. You can easily distinguish the superconductivity of the nematic superconductivity results, like with the angle resolved resistance, through resistivity. So you can easily find and discuss the results through the transport measurements. And this is the future scope of this work. So if we make a heterostructures and the heterostructures like of the strained materials in the because of the in the strained, like if there is a strain in the materials, that this breaks not always in the rotational symmetry states. So that's why we can tailor the signatures, and signatures tends to into the nematic superconductivity. Like of the stations by the electric field and many of the others parameters, like with the magnetic field we cap magnetorestrictions, like the case it may be that in also the magnetorestrictions the um, there is no symmetry always present like the rotational symmetry, so that's why also showing the nematic superconductivity results. And second is one of the important is that the nematic superconductivity may coexist or interplay with the topological phases, especially in topological superconductors, which is very less unexplored yet. So the nematic superconductors along with the topological materials, because the topological materials are very much affected by the superconductors if we make a close connection of the superconductor and topological materials. So the topological materials are very much affected due to the surface states. So that's why they either they break the superconductivity, and if it may also that the topological materials, they are the high robust mobility materials, they many times they also break the superconductivity, and it may be to enhance the inverse proximity superconductivity, which have very less results in the literature to have been shown in the inverse proximity superconductivity. So this is maybe the future scope of this work. So now the thank you.